Welcome everyone to our 9 a.m. press conference. This one's on California's epic drought as viewed from space. And our speakers in this order: Jay Famiglietti from NASA Jet Propulsion Laboratory and UC Irvine in California. And Tom Painter, he's also with NASA JPL, which is in Pasadena, California. Matt Rodell, he's with NASA Goddard Space Flight Center in Greenbelt, Maryland.
Good morning, everyone. Thanks for joining us. A recent paper in Geophysical Research Letters found that the California drought is the worst 3-year drought in the last 1,200 years. While paleoclimate studies help put this current Millennium California drought into a historical perspective, a new breed of satellite and aircraft sensors is now helping us characterize the current drought and to quantify its impact with progressively greater accuracy. These sensors are technically known as geodetic sensors, and they measure with unprecedented precision how the shape of the Earth, its surface height, and its gravity field change over time. Since one of the primary drivers of these variations is the change in the water stored on land, our research has shown that we can invert these measurements to provide new estimates of important quantities such as the changes in total water storage, changes in groundwater storage, or changes in the snowpack. Today, my colleagues and I will present new findings that show how we at NASA are using these sensors and integrating them into computer models to better characterize drought and estimate water losses in ways that have not been previously possible. I'll start off by presenting new results from NASA's Gravity Recovery and Climate Experiment, or the GRACE satellite mission. This work shows that it's now possible to explicitly quantify previously elusive drought indicators, like the beginning of the drought or the end of a drought, and importantly, the severity of the drought at any point in time. That is, we can now begin to answer the question, how much water will it take to end the drought? We show that for the current drought, that quantity peaked in 2014 at 42 cubic kilometers of water. That's 11 trillion gallons, or about 1.5 times the volume of Lake Mead. So no, the recent rains have not put an end to the current drought at all, but they are certainly welcome. Our colleague Dan Cahan had to withdraw from the press conference because of an injury in his family. His wife tore her Achilles tendon, but he would have shown how the Global Positioning System, or GPS, can track crustal uplift due to the drought and can be used to enhance some of the measurements that we get from GRACE. The NASA Airborne Snow Observatory, or ASO, is providing first ever high-resolution measurements of the volume of water stored as snowpack in mountainous regions. Using an airborne LiDAR, Tom Painter will show ASO measurements in the Tuolumne River Basin that increase the spatial coverage of snowpack observations by a factor of only 39 million relative to traditional ground-based measurements, which Tom will show you are made by guys wearing cross-country skis and snowshoes. One of the key findings of the 2014 ASO campaign is that previous estimates of snowpack were 100% too large. Integrating this information, like GRACE, for example, into an experimental drought mapping framework gives a more holistic view of the impact of drought on water availability, including on groundwater resources that are typically ignored in standard drought indices. Matt Rodell will discuss this activity, which is now used to inform the U.S. Drought Monitor on the status of groundwater levels. He'll show us that current groundwater levels across the southwestern United States rank in the lowest 1 to 10% since 1949. So we'll go through our presentations, and then I'll come back for one summary slide, and then Peter Weiss will be back up here to handle questions. Okay, since its launch in 2002, the NASA GRACE mission has been mapping changes in Earth's gravity field, effectively working like a scale in the sky. That has allowed us to weigh and map out the regions around the world that are gaining or losing water mass each month. Our most recent data for California, and this is really for the Sacramento and San Joaquin River basins, reveal just how devastating the drought and really the last 12 years have been on California water resources. This slide shows the ups and downs of total water storage, that is, all of the snow and the surface water and the soil moisture and the groundwater combined in the Sacramento and San Joaquin River basins, which are really the water workhorses of the state. If we focus on the current drought, which is the last 3 years going back to 2011, we can see that the basins have lost, or we calculate that the basins have lost 15 cubic kilometers of water each year going back to 2011. That's 12 million acre feet, or 4 trillion gallons, in each year of the last 3 years. That's more water than all 38 million Californians use each year for domestic and municipal use. In a later slide, I'll show you that 2/3 of these losses are coming from groundwater depletion in California's Central Valley. These colored panels show how we can map out the drought using GRACE, and these represent the dry seasons of 2006, 2009, and 2013. Now that we can chart these monthly ups and downs of the total water storage, as shown in the top panels, that's just a repeat of the one that I just showed you, we can begin to understand the average range of wet and dry season conditions, and that's what's shown in the middle. The middle panel is just sort of the seasonal average of the upper panel. Average January, average February, average March, and so on. And so when we compare the two, we can quantify the deviations from normal wetness conditions, for example, under really wet conditions here, or deviations from normal dry conditions like we see here. And that's what I've plotted down below here. So we're looking at how much wetter than normal wetness conditions we are for the high points, how much drier than normal dry conditions we are on the low points, and that's the bottom panel. That's what I call, or we call in our research group, the total water storage deficit at any point in time that is required to be replenished to get back to normal conditions for that time of the year. Okay, so this total water storage deficit analysis allows us to very effectively quantify for the first time when a drought period or deficit period begins, when it ends, what its instantaneous magnitude is, meaning how much water do we need to get back to normal dry conditions, normal conditions for that time of the year. And that number is, excuse me, Tom, I don't want to shave off your nose.
Laser safety.
That number peaked earlier this year at 42 cubic kilometers. That's 34 million acre feet, or 11 trillion gallons. That's the equivalent of 10 Lake Oroville. So it would take 10 Lake Orovilles to bring us back to normal conditions for this time of the year, which is we're still talking about dry season conditions. But it also means that we can begin to answer the question, when will this drought be over? And the answer would be when we replace these 42 cubic kilometers, when we satisfy this deficit of 42 cubic kilometers. We can also see that over this time period, the magnitude of the droughts has been increasing. Okay. This is an animation of these ups and downs of water storage. The reds are the drier than normal average time periods, where the averages for this period 2002 through 2013. And the blues are wetter than average. We're about to go into the drought period. So it gets very, very red. And so we can map this stuff out spatially. And that drought pops out very strongly. In my last two slides, I want to focus on how much of these overall losses are coming from groundwater. This black line shows that our latest monthly estimate of groundwater storage changes in the Central Valley, and the 2006 through 2010 and the current drought really pop out prominently. Since 2011, California has lost, or the Central Valley has lost 10 cubic kilometers of groundwater each year, for a total of 30 cubic kilometers, or a Lake Mead's worth of groundwater. These colors in the background show the federal and state allocations of surface water from the Sacramento and San Joaquin rivers and the Bay Delta to the rest of the system, to the rest of the state via this system of canals. And they're shown as a percent of full allocation. Right, so this is a year in 2006 when we get a full allocation of surface water. Okay, in contrast to right now, we've got 0 and 5% in 2014, and nothing allocated yet. Only the State Water Project allocations come out right now, and that's 10%. And so what we see, the reason for showing this is the close correspondence between decisions about surface water allocations and what happens with groundwater. When there's a lot of surface water, groundwater recovers. When surface water allocations are cut, we hit the groundwater pretty hard, right? It gets wetter, and groundwater recovers, and it gets dry, and here we are now. So we can only imagine where this groundwater is going to end up. And so to finish with my last slide, as you may gather, then we probably can't keep doing this forever. This slide shows the cumulative groundwater depletion in the Central Valley going back to 1962. And it's an extension of a figure from Claudia Font's 2009 USGS report. And here we've combined that USGS data in red with our GRACE data that I've just shown you in green. And so we see a very clear picture of the unsustainable path that groundwater use on the Central Valley is on. We see a bit of recovery in these wet periods that are shown in the dark blue, right? Or in the lighter colors, sort of moderately wet, moderately dry, and light gray and light blue. Wet periods are shown in the dark blue, and the droughts are shown in tan. And so we see in the wet periods we get some recovery and then big decline in drought. Some recovery and then big decline. Some recovery, decline, and so on. So we're on this pattern, which to me is really the definition of unsustainable. So clearly the amount of groundwater extraction vastly outweighs the amount of replenishment. So the current long-term downward trajectory is quite clear. Without intervention, like a tennis ball bouncing down a flight of stairs, the ball always ends up at the bottom. I'll pass it on to Tom.
Okay, great. All right, thank you. So 2014 California snowpack was the worst on record. It duked it out with 1977 through the year, but finally won out. 1977, though, at that time we had half the population in California that we have today. Now, understand that this information about these records comes from snow pillows and snow courses, which are individual points, and they're located largely at the lower to middle elevations. So we haven't really known what's going on in the higher elevations, and therefore we haven't known the exact distributions of snow water equivalent until the Airborne Snow Observatory, which I'll describe in a moment. This is showing a pair of images from Januaries on consecutive years, just to be illustrative of the impact. So with reduced accumulation of snow cover, it also usually comes with reduced aerial extent of snow cover. So not only does that mean that we have less distribution of snow water across the landscape, but we also have more absorption of sunlight by the surface. This comes through the so-called snow albedo feedback. There's more absorption of sunlight at the surface that is re-radiated back to the atmosphere and heats the atmosphere. Then we also, with that heating of the surface, we also have a reduction in soil moisture. And with that reduction in soil moisture, that puts us in a position which, when we do finally start getting a lot of snow, it takes that much longer for us to get the runoff, and it's that much more difficult to fill the reservoirs. The other issue that's posed by that is the vulnerability to wildfires. And the last 2 years, we've had the King Fire and the Rim Fire, two of the largest wildfires in California history. This movie will show the spatial distribution of snow water equivalent in the Tuolumne River Basin above the Hetch Hetchy in 2014. And you can see this complete mapping that we do. So as Jay mentioned, we have 39 million times more coverage than what the snow pillows and snow courses give us. We essentially have a snow pillow every 1.5 square meters across the landscape. So with this information, we're starting to understand the snowpack and what it is that we haven't known about the higher elevations. And one of the main things that I want to point out to you today is that the map here on the left shows the errors of what has been our previously best estimate of spatial distribution of snow water equivalent, and this has come from a combination of modeling and interpolation and extrapolation from the point measurements, but never with any strong validation. And what it shows is that at least in 2014, it would have suggested that we had twice the water that we actually had. And primarily that's coming in the higher elevations above where the snow pillows and the snow courses lie. So with this new information and spatially complete information, we're able to better understand our water resources and better understand the climate system. All right.
Okay, thanks. As Jay described, the GRACE satellites are providing information on drought that would be impossible to collect using ground-based observations alone. And what we're able to do is to take the GRACE data and combine those with other observations, both surface observations and satellite observations, things like precipitation and solar radiation. We combine those within a sophisticated model of the Earth's surface, known as a land surface model, and we're able to come up with better information on drought and on wetness conditions in general. So what these results look like are shown in the top panel here. These are drought indicators that come from combining the GRACE data with other satellite and ground-based measurements. And you can see that we have not just a trusted water storage observations like we would get from GRACE, but we can divide it up into surface soil moisture, root zone soil moisture, which is the water in the soil down to about 1 or 2 meters depth in the groundwater storage. These are maps from December 1st this year. We do have newer maps on our website, but we had to deliver this product last week, so they weren't ready yet. Compare these maps on the top with the U.S. Drought Monitor on the bottom. The U.S. Drought Monitor you probably know from the Weather Channel or the back of USA Today. And this is the U.S. Drought Monitor for December 2nd. And you can see that the general patterns are about the same, but there's really more high resolution spatial information in these new maps. And in fact, the Drought Monitor now relies on these new maps. We provide them to them on a weekly basis. The U.S. Drought Monitor authors use these GRACE-based maps to help improve their map, and without our maps, they would have no information on groundwater, which of course is a critically important resource, but also a useful indicator of drought. I'm going to animate the maps that we've produced. Oops, let me go back. Jay's going to animate it. Thank you, Jay.
Welcome.
Okay, so first, let me just say what we're showing here. These are the drought maps we produced. The left is root zone soil moisture. The right is shallow groundwater. Starts in 2002 and goes up to present or near present. You'll notice first that on the left, the root zone soil moisture changes much more quickly than the groundwater. That's because it's in direct contact with the atmosphere, which is the input that really drives the whole system. As we go through time here, you'll see we get to 2007, 2008. It's going to be, oh, Jay, can you start over?
Sure.
Thanks, Jay. Okay. So again, as you gaze upon this, you'll see that the droughts and the wet conditions come and go. So these are all natural phenomena. The droughts come, the droughts go, and they sort of move slowly about the landscape. When we get to 2007, which we're hitting now, and in 2008, you'll see it get really dry in the southeastern U.S. You may recall that drought affected Georgia and that area. As we get a little later on into 2011, which is coming up soon, you'll notice it gets really wet in the north central U.S. There was flooding at that time. You also see it get very dry in Texas right about now. That was a major drought they had in 2011. As we go into 2012, you see the whole country really get red. You may remember the summer of 2012 was a massive drought. 2012 was a massive drought across the U.S. And then as we get into 2013, 2014, hope you noticed it got really dry in the southwestern U.S. and particularly California. And you can see here, this is the last date, December 1st. still really dry across California. This is prior to the rains, but as Jay mentioned before, the rains that we've gotten, while they will probably improve this condition in the soil moisture, the groundwater takes much longer to respond to either a wet or a dry anomaly. So it's going to take some time before the groundwater levels come back up to normal. Similarly, we need more snow, and we need and the surface water bodies need to refill. So it's not just a soil moisture condition, and that's one of the main reasons why it's so important that we're providing these maps to the U.S. Drought Monitor, which prior to that really relied on a lot of soil moisture and surface information. So I'm going to pass it back to Jay for closing remarks.
Okay, thanks, Matt. So just to summarize some of our key points, NASA scientists are using new satellite technologies and integrating them into the U.S. Drought Monitor to characterize drought and estimate water losses with greater precision than has been previously possible. New results from the GRACE mission have shown us that since 2011, Sacramento, San Joaquin River basins have lost about 1.5 times the volume of Lake Mead. 2/3 of those losses were about 10 cubic kilometers per year. Were from groundwater depletion in the Central Valley, so that the Central Valley has lost a Lake Mead's worth of groundwater since 2011. A new total water storage deficit drought analysis using GRACE data can now quantify the beginning of the drought, the end of the drought, and the magnitude of a drought. And the peak total water storage deficit in California occurred this year at about 42 cubic kilometers. NASA's Airborne Snow Observatory, ASO, is providing first high-resolution snowpack measurements in mountainous regions. It shows that previous measurements of snowpack are off by a factor of 2 in California's Sierra Nevada range, and integrating the NASA GRACE data into an experimental drought mapping framework provides new information on groundwater storage to the U.S. Drought Monitor, and it reveals also that the groundwater levels across the southwestern U.S. Rank in the lowest 1 to 10% since 1949.
Okay, thank you very much, speakers. We'll open the floor to questions.
Rick Lovett, freelance. I have a question for Dr. Rodell and one for Dr. Famigletti. For Dr. Famigletti first. If these are off by a factor of 2, and they've always been off by a factor of 2, then it seems like all the history with figuring out how much runoff there is also, so does it change how much moisture actually reaches the reservoir, or is it just changing our model that produces the same result?
Sure. So let me pass that question to Tom, because that factor of 2 is really about the snowpack measurements.
You're talking about the snowpack, right?
Yes.
Yeah. So the reservoir managers tend to use their snow pillows, snow courses, their information, and their empirical functions, and those are based on the legacy of measurements that they have, 30+ years. But in the last decade, there has been a new National Weather Service modeling effort called SNOWDAS to produce these spatially complete maps of snow water equivalent. And what we're finding is that those which are used widely now, not necessarily in the water management, but more broadly in hydrologic modeling, and has been investigated with resource management. Those are this year we're off by a factor of 2. So, but what we're really finding is now how much water is actually in the snowpack relative to how much we're getting out of the mountain basins, and it's giving us a much better handle on how those mountain basins respond, and in turn that will give us an idea not only during droughts but also during a changing climate.
And my question for Dr. Rodell is, how do you tease out, thank you by the way, how do you tease out the difference between shallow groundwater and root zone water out of the GRACE data, and also how shallow is shallow?
I may have to talk with you more about this after, because it's actually, I could spend a half hour trying to explain it, but we have a model of the land surface and all the processes. So the model has different layers of soil, and it has a representation of groundwater, and has a system of equations that tells you what happens after the rain and sunlight hit the surface, what happens to that rain and that energy or snow, and the water percolates down through the soil, eventually makes it to the groundwater, and this is all simulated within the model. So basically the model is doing a simulation of all this on its own, and then we use the GRACE data to help constrain the model. So it basically makes the model better. We have an estimate from GRACE, we have an estimate from the model, and using information on the uncertainty in both, or combine them to come up with an optimal estimate. Oh, well, so in the model, we're talking about the water table. So basically, when you drill down, the first water you hit. So we're not talking about the deep confined aquifers.
Harvey Lyford, freelance. Sorry about the voice. First, I'd like to thank JPL for providing an excellent packet here with copies of the slides. My question for Dr. Painter is, could you say a little more about ASO? We saw an image of a part of an airplane. Is it just one plane or a suite, or how does it work?
Well, you're asking the right question. So right now it's one plane, and out the belly of the plane we have two instruments pointed. One is a scanning LiDAR, so a high-frequency laser pointer that tells us how far away the surface is, and then differencing between snow-free conditions and snow-on conditions, we can tell how deep the snowpack is across the entire landscape. And the other instrument that we have on board is an imaging spectrometer that measures reflected sunlight, and about 90 to 95% of the energy that goes to melting mountain snow comes from absorbed sunlight. So having those measurements of how dark or bright the snowpack is, and there is considerable interannual variability in that, tells us how quickly the snowpack is going to melt. Now, the one airplane aspect of this, there's considerable interest throughout the West as well as internationally for these kinds of data, and so we're working with the state of California as well as Colorado River entities to start spinning up more aircraft. Ultimately, we want to see snapshots of the entire Sierra Nevada with this comprehensive information, and we're headed in that direction.
Hi, Kit Stoltz, Santa Barbara Independent for the panel. Earlier this year, the Washington Post, I think it was in February, reported that the Obama administration was looking at pictures of the California snowpack, and that helped motivate their decision to take action on climate. Did they contact any of you and talk about these issues?
They did not contact me directly. Our NASA program managers were here, but I think they're gone now. But that kind of information tends to come from higher up in NASA. But almost certainly it came from the kinds of information that we're providing.
But, we were just contacted in the same manner from the top down about the GRACE groundwater work, and provided information to the President's Council of Advisors on Science and Technology and John Holdren.
Yeah, I'm Dave Perlman from the San Francisco Chronicle. Jay, when you talk about the volume of Lake Mead, are you talking about it in terms of its normal capacity, or?
Yeah.
Okay.
I'm thinking around 30, between 30 and 35 cubic kilometers.
Okay.
So, yeah, that's
and the other is another clarification thing. All these sort of inconceivable, to the normal people, trillion gallons of water.
Yeah.
Does that translate into acre feet? Is there a way of converting it to acre feet?
Right.
So, we're more used to that.
Yeah, so I showed the time series of the GRACE data. It showed that we've lost 15 cubic kilometers per year for the last 3 years.
Yeah.
So it's 45 cubic kilometers. That's 36 million acre feet. That's 12 trillion gallons. So each year it's a third of that. So it's 15 cubic kilometers of water. I can do the conversions with you later. Yeah,
and that's
right,
more than twice the annual flow of the Colorado River.
Yeah. Okay. Thanks.
I get them confused all the time.
Do we have any questions from the chat?
No.
Do we have any more questions from the room here?
Jonathan Amos, BBC News. GRACE is an amazing tool. What happens when the mission ends? It's quite old now.
We cry. No, there's, how are you? Good to see you again. There's the GRACE follow-on mission is planned for 2017. And so we hope there'll be at least a year of overlap. And the GRACE follow-on mission is pretty much just like the current GRACE mission. So we're hoping for continuity of the measurements.
More questions? None from the chat? Okay, that wraps it up. Thank you, speakers, and thanks everyone for participating.